This video is brought to you by mywayteaching.com.
In that, the next one is thermochemical equations. Okay, what we are studying: enthalpy change, delta RH of a reaction, reaction enthalpy. In that first we have studied standard enthalpy of reaction, enthalpy changes during phase transformations, and the third one is standard enthalpy of formation, and the fourth one is thermochemical equations. A balanced chemical equation together with the value of its delta RH is called thermochemical equation. So what do you mean by thermochemical equation? A balanced chemical equation together with the value of its delta RH is called thermochemical equation. We specify the physical state of the substance in an equation. Okay, and in the equation, for example, I will write down C2H5OH plus 3O2, that is 2CO2 plus 3H2O of liquid. Okay, so here delta RH is equal to minus 1367 kilojoule per mole. The above equation describes the combustion of liquid ethanol. This is ethanol. Okay, at constant temperature and pressure. The negative sign of enthalpy change indicates that this is an exothermic reaction. Here negative sign indicates this is an exothermic reaction. It would be necessary to remember the following convention regarding thermochemical equation. Conventions regarding thermochemical equations. Okay, the first one, the coefficients in a balanced chemical thermochemical equation refer to the number of moles of reactants and products involved in the reaction. The coefficients in a balanced thermochemical equation refer to the number of moles of reactants and products involved in the reaction. Products involved in the reactants. Next, second one, the numerical value of of it refers to the number of moles of substances specified by an equation. Standard enthalpy change delta RH of theta will have units as, this is having the units of kilojoule per mole. Okay, next, to illustrate the concept, let us consider the calculation of heat reaction for the following reaction. Illustration. Okay, so in that Fe2O3, consider plus 3H2 of this, which gives 2Fe3H2O. So from the, we know that and we can get, we will get standard enthalpy of fusion. Okay, so standard enthalpy of this is standard enthalpy of formation. We find formation for H2O minus 285 point minus 285.83 kilojoule per mole, and that is for Fe2O3 for solid is equal to same standard enthalpy of formation minus 824.2 kilojoule per mole. Also for Fe of solid is equal to 0, and standard enthalpy of formation for H2, this is 0 as per the convention. Okay, then 3 minus 285.83 kilojoule per mole. Okay, then minus of 1 24.2 kilojoule per mole. Okay, this is minus, okay, I write here. So now the answer is minus 33.3 kilojoule per mole after the calculation for this one. Okay, note that this is, note that the coefficients used in these calculations are pure numbers which are equal to the respective stoichiometric coefficient, the unit for delta RH. Okay, so is kilojoule per mole, which means per mole of reaction. Okay, next, the third one, when a chemical equation is reversed, chemical equation is, when a chemical equation is reversed, the value of is reversed in sign. Okay, so this is reversed in sign. Okay, this is the thermochemical equations and the three conventions. Okay, next is Hess's law of constant heat and summation. What is Hess's law of constant heat summation? We know that enthalpy is a state function, therefore the change in enthalpy is independent of path between initial state and final state. If a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the overall reaction may be divided at the same temperature. Means, consider if a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the overall reaction may be divided at the same temperature. Okay. See, in general, if enthalpy of an uh, okay, I went to explain you by taking the example for the Hess's law of constant heat and summation. It means, uh, let us consider the enthalpy of Hess's of constant heat summation, and first consider here, let us consider the importance of this law with the help of an example. I will explain you it with an example. Okay. Okay, let us consider the example of Hess's law of constant heat summation. Okay, so consider this graphite. Okay, see this as a graphite plus half of oxygen, which gives a carbon dioxide. Okay, so although carbon dioxide gas is the major product, here this is the major product. Some carbon dioxide, this is CO, carbon monoxide, this is CO2, means gas is always produced in this reaction. Therefore, we cannot measure enthalpy change for the above reaction directly. However, if we can find some other reactions involving related species, it is impossible to calculate the enthalpy change for the above reaction. Let us consider the following reactions. So consider following reactions. Okay, here consider that as see graphite plus oxygen, which gives a carbon dioxide gas. Okay, so delta RH is equal to minus 393.5 kilojoule per mole. This is equation 1, and this one of this gives, this is equal to minus 283.0 kilojoule per mole. Okay, so this is the equation 2, and we can combine the above two reactions in such a way that as to obtain the desired reaction to get 1 mole of carbon monoxide on the right. So we reverse the equation 2. In this, heat is observed, so we are reversing the equation 2. Equation 2 we are reversing it, so you are getting this one, so that if you are reversing that, you can get this as plus 283.0 kilojoule per mole. Okay, so adding equation 1 and 2, this is, we call this as equation 3. So adding equation 1 and 2, sorry, 1 and 3, we get this one. So delta RH minus 393.5, this one is plus 283, so we are getting minus 110.5 kilojoule per mole. In general, if enthalpy of an overall reaction, if enthalpy of an overall reaction A to B along one route is delta RH, and and delta RH 1 comma delta RH 2 comma delta RH 3, representing enthalpies of reaction leading to same product. Okay, representing enthalpies of reactions leading to same product. B along another route and B along another route. So then we have delta RH is equal to delta RH1 plus okay, and it can be represented as A, this as B, this as delta RH, okay. So delta RH 1, 2, 3 and you are obtaining delta RH. This is the Hess's law with an example.